little record on here. Hi, welcome. Welcome to a live recording session. I've never actually done anything live before, ever. I mean, like everything I do is sort of impromptu in a lot of ways, but what I am essentially doing right now is I'm going to solder up some circuit boards live, if you will. One of the things that I will be doing here, let me load up on my screen just in case I need to get down to it. Let's see here. Oh no, I need to do a login for this here. Sorry, I thought I was prepared. I thought I actually was sort of prepared here, but I'm not. Let me log into my my software for my PCB editing software. No, now it's asking me. This is the first time I've ever seen it ask me to make sure with pictures that I am not an actual robot. So that's kind of nice. You know? So let's see. What I'm doing right now is off the screen. I am loading up my the schematics for this particular circuit, and that's only in case I need to be able to look at it here. I don't think I'm going to need to be able to look at this here, but it's one of those things that you never really know until you actually go and you try to do it here. So I think, is that you? I think that's you. I think that's you. Okay. Yep, that sure looks like it. So here, let me kind of whap this onto the screen. Are you going to be okay with this computer? Again, I've never done anything live. I'd be surprised if this worked to everything that I would actually want it to be able to work to. Here we go. Okay, so hopefully you'll be able to see the schematic here. So the schematic of this is, like I've kind of done a series of videos about this a while back. Let me get my streaming thing back on, kind of back going here again. So also let me just double check to make sure I am going live. Again, I've never done this before. In fact, I'm actually going to say this. Never done this before. This should be fun. There. Hey. Yeah. So, okay. So anyway, what you were looking at is the circuit board that I've built, the schematic for the circuit board, and I've got this whole thing powers by a 3-volt source, which actually, come to think of it, that's the one thing I did not grab are extra clips, or extra little battery clips. So I might have to go and find those off screen here in just a little bit. We've got a battery. We got the microphone, which is here. This is a MEMS-based microphone. The microphone goes to a coupler circuit. The coupler circuit, consisting of a capacitor resistor, filter out the DC bias off the microphone, and then an amplifier circuit. Actually, an inverse amplifier circuit is what boosts the signals of the microphone up so that I can get to acceptable levels. And then finally, a comparator network via a series of operational amplifiers and other resistors, and I think a little capacitors in there, as well as some LEDs that go on the thing all the way out. The goal is to make a couple of these things so that they're actually able to work kind of for the students here. So we're going to start by building these the exact same way we built the previous one. This is what we built. Hi, hey, how's it going, everyone? How's it going? Feel free to say something in the chat box at any point here. Again, I've never done this before, so this is kind of a fun thing, is what it is. All right. So what do we got? I'm gonna actually I have enough to build 3 circuit boards. Is actually what I've got. And kind of the goal of what I'm going to do here is I'm going to build them to the point where they're actually working. And then I'm going to be a total turd later on and actually kind of put some things incorrectly on here is what's really going to happen. So let's start for this circuit here. I think what we're going to do is actually build each circuit part in tandem with one another. So I'm going to grab my pair of tweezers. I've got a pair of OOSA Technic tweezers. These are by far my favorite type. I can't actually honestly say enough about this particular pair of tweezers. I mean, I order them for the folks at class. I order them for myself. Like, I order these just in general. They are marvelous, marvelous tweezers. They are not so sharp and pointed that they can easily bend. They can grab small things when I need to. They are by far one of the best tools that I have possibly ever really used. So I've got my micro-tip soldering iron is what I've got right now, which should be okay, even though a majority of the parts I'll be working with are kind of bigger in terms of their overall size. Let's grab some capacitors to start with, because I'm going to start kind of over here on the left-hand side of this circuit board, assembling C1, C2, and C3 for each one, which actually all happen to be, the exact same value of 1 microfarad. C1 and C2 are what we call bypass capacitors. And I'm kind of preparing these here. I'll move these kind of capacitors up. These are, see these guys right there? Those are 0805 bypass capacitors. Well, with the exception of C3. C3 is actually not a bypass capacitor at all. C3 is the filter capacitor, which is actually going to filter out some of the signal that is coming off of the microphone, is what it's doing. That's what's helping. That's part of the coupler circuit. That's actually helping to reduce. That's actually part of the coupler circuit. That's helping to reduce some of the DC bias that the microphone normally outputs, which is somewhere around the range of, I think, like 0.8 volts or something like that. It's something around, at a 3-volt battery bias on the microphone, it's somewhere around, I believe, 0.8 volts. So here we go. I've got the first circuit board. I'm actually going to give this a little bit of a turn here and trying to do as much of this on screen as possible. The solder that I'll be using is lead-based solder. It is, let's see, the stuff that I've got here, and I'm going to start with the smaller stuff to begin with here, is AM 1063 lead 37 based solder with a diameter of 0.015 inches. So probably some regular lead-based soldering before. I don't know if you all used anything kind of similar to that at all with kind of what you work on. So now we're going to come on down, and I am recording this session, by the way, so I will at some point have a chance to kind of repost this onto my own YouTube channel just a little bit later on. And also, just again, fair warning, I have never done a live session before. This is very, very very new to me. The reason I'm doing it kind of on YouTube is just so because I wanted to have a chance for not only for my class to be able to potentially view this, because actually one of their classes is going to be to find the mistakes once I prove to myself that I've actually got a working circuit. Not only to prove that, but also to just to talk a little bit about circuits and everything like that, to have a little bit of a video in case anyone wants to sign on and see a little bit more about how electronics are actually assembled. My temperature seems a little low. It seems like it might be a little bit low. That's okay. That's okay. For what's my temperature? My temperature is actually currently at 610 degrees Fahrenheit on my soldering iron, using my micro-tip soldering iron, my KN micro-tip soldering iron. Very easily my most favorite and cherished micro-tip out of all of the soldering. Now I'm actually, one of the things I'm going to do real quickly is I'm going to adjust my lens filter just a little bit, because, not my lens filter, I'm sorry, my eyepiece. That's what I've got. It's my eyepiece. I've got a little bit of some cleaning solution just off screen. Hey, come on, you. What do you not want to... Man. You all hear that? Now, maybe I don't have any cleaning solution off the screen here. I'm not sure about that. Ah, there we go. That just took... Maybe there was a little thing in there or something like that. Actually, one of the things that they released recently on... I think it was Leica actually released this recently. Leica released some information talking about how important it is for people who work in with microscopes to be able to make sure that their microscope is cleaned. I mean, if you think about this, how many times have you been told by people, don't touch your face, don't touch your, oh, geez, why don't you stay down over there? Thank you very much. Don't touch your face, don't touch your eyes, don't touch your anything like that. And here you go, you're putting your microphone on the, oh, we've paused. We've paused our live session, I think. At least I think it's paused. I have no idea. I have no clue. I'm assuming that this is paused right now. Don't officially know if this is paused at the moment. We're going to kind of find this out. Finding this out together. Finding this out together. So let's put a little bit of some solder on C3. Has this really paused? Oh, gosh. I don't understand live streaming at all. Oh, and there's my email. That's the other thing you probably wanted to hear bounce around in the background. Let me go and turn that off. Because there's definitely... Okay, gotta carefully turn that off there. There we go. Is that a little bit better? I don't know. I don't know if I'm still broadcasting or not. I've got no idea. I really don't have any clue whether or not I'm even broadcasting live right now. This all just could be, well, I am recording it though, so you've got that kind of going on right now. Just kind of a nice thing. So, don't see anything in the chat at the moment. So it is possible. I mean, I also have nothing but a a standard basic internet service might be the right way to kind of phrase what that is. So that is probably in a nutshell probably the easiest way to phrase what that is. Oh no, is that just me? Is that me? Am I having a problem with something here? Am I not doing something right? I might not be doing something right. I might actually not be doing something right. I have no idea what's happening here. Is there something going wrong? Oh no, the whole thing just cut out. That's wonderful. Is it still working? Can I return? Live now? Is this, I mean, can you all still see me here? I've got no idea. Are you all still there? Oh, hi. There's people who have actually joined. Hi there. My whole thing just decided to go and do a delay. Hey, Chris. Hey, Bill. I'm sorry about that. The whole YouTube software thing just went down in a flourish and a flurry is what it went down in. Okay, so I've got my capacitors attached to that one. I'm so sorry about that. Again, I'm new. I'm complete. What's the right word? Noob. That sounds about right. Yeah, noob. Is what that's what's going on here. Yeah, noob is what that is. So I'm so sorry about that. That was a that was a thing. Is what that was. All right, let's now we got the second circuit board. Let's put got a little fluxing agent on my test pad. Yeah, my circuit board actually has several test pads on it, but I've noticed that I noticed this the other day. My T plus test pad is actually the same thing as another test pad that I've got elsewhere. So I've got one ground and two identical VCC, which is like in terms of the circuit board, it's actually just above the actual actual circuit. Now, Bill and Chris, you're actually here right now. What you are looking at is essentially what is the capstone students project is actually what you're looking at. One of the things that we are reviewing with them is we are going to be reviewing with them how to do troubleshooting. So we are having them build something what's called an out-of-control action plan, an OCAP, which is, you know, a one-letter R off of, you know, what it really kind of is at the end. It's when something goes bad, it's the documentation that says, what do I do when it goes bad, is what it is. Out-of-control action plan. That actually comes from, my bud, the one of the new MEM staff member, Greg, who uses that at used that at Motorola, which was a series of documents that all said, okay, if for instance, if one of these capacitors has a short circuit on it, you know, if one of these capacitors decides, you know, not to work for some reason, what is the correct plan of what to do? How do I see it? Like, how do I know it's happening? How do I know something actually is not working correctly, and what can I do about it? What are the tools? So it's essentially kind of like a series of quality operating procedures, with the exception of the OCAP, which is, I mean, the joke is it's one letter short of crustacean is might be the nice way to be able to phrase it, keeping everything PG-13 and everything like that, you know, or PG something. I don't know. I try to make sure that there's I don't specifically state that these videos are like meant for little kiddos, but I'm not exactly getting angry and throwing out lots and lots of words that will get you thrown out of a baseball game if you say it to an umpire. You know, that kind of stuff. So I leave that for when I'm in class. Is usually the right time for being able to say something like that. All right, and then we have the third board here. Actually, you know what I might do? You know what I might do after this? I might just attach all of the capacitors after this, because C4 needs to still be attached as well. So there is a little bit of some of that. I'm applying this fluxing agent, this Amtech fluxing agent, which is this kind of this tackier flux. I like using the tacky flux in comparison. Like, I've seen some other fluxing agents. In particular, I think there's one at the college which they use in our other soldering and fabrication laboratories. And the reason I don't like that fluxing agent as much, number one, this coats leads really, really well. Like, so for things that have a lot of height, in particular, this coats them very, very well. Number two, I can reuse this fluxing agent for a long, long time. Like, if I had to continuously keep using this flux to solder parts down to a board, I mean, this is going to stay here. This is going to stay here for, I mean, lots and lots of uses, very, very easily. You notice that when I am, oh, that's not good. You notice that I am making sure that the capacitor is getting heated up to the point where it's actually going to have solder that flows on top of it. This also comes with a very, very steady hand of mine where, you know, just keep making sure that I'm kind of applying a couple of things at the same time. Number one, I'm making sure that my wrists are flat on the ground while I'm doing all of this. I'm trying to make sure that that my wrists have as much stability as possible. Number two, I am applying a very small amount of force down onto the board and onto the tweezers when I'm moving them around. Oh, excuse me. Which helps to keep the tweezers stable. But yeah, so it really is kind of all about the steady hands when it comes to this. So the tacky flux. So I can use it a whole bunch of times. It covers things that have 3 dimensions, or has bigger. Like for chip resistors, it works about as good as the same stuff, but or the stuff that we've got, like the more oh gosh, what would be the right term? Low viscosity stuff that's inside of the fabrication laboratory. It works just about the same with that. And I know, Bill, you've probably used that stuff, refilled that stuff from time to time. It's pretty watery. You know, like this other fluxing agent, you really got to kind of, you can really just use an eyedropper almost as you will to just kind of dispense the whole thing out, if you really wanted to. So, all right, that's all. So that's all three of the chip resistors that are on these boards. I'm going to leave R1 blank. R1 is actually just meant to bypass the switch if I don't want to use the switch. If I don't feel like using the switch, I can actually completely bypass it. But just while I can finish all of the capacitors, just because it's all kind of in one spot. And again, the reason I am building these boards is because the goal is going to be right now the MEM students all have a for their class, they have a homework assignment, a homework. They have some things that they have to do to provide for an out-of-control action plan. And we've given them a variety of scenarios to think about for their out-of-control action plan. And one of the things that we want to just, work with them on is, how can you tell, how can you measure whether or not something is working? Yeah, exactly. Yeah. Yeah, by the way, I think there's like a 15-second delay or something like that. So I am reading chat. So if you see I see the basically water, not a fan. I'm kind of looking back and forth between that. So if there is a little bit of a delay in terms of me responding back, that is entirely my fault for what that is. So, but anyway, yeah, so these boards, they're being assembled right now because I would like to be able to assemble these correctly to the point where they're working, and then I kind of want to screw them up and see with the students if their OCAPs have enough material to cover the search. Like, like something is going wrong. I'm taking a look over the whole thing. Can I tell exactly what's going wrong with the board? What's the fix? What are their tools to fix it? And this is very much it is one thing that engineers typically don't like to do, is use use verbiage of things and actually write some stuff out. I can't even tell you myself how much I personally dislike writing things out sometimes. Like, sometimes it's one of those, like, and everyone kind of gets like this every once in a while. It's like, I know my way of doing things. I know the way I like to do things. And at the same time, why do I got to explain it out to someone in terms of what it is that I'm doing? I can actually, one of the things is this Zoom okay? Is this out okay? Far enough okay? I see Chris. Oh, thanks. Delay is pretty normal across all these types. Yeah. Is it? I think so. It's one of those, like, since I've never done it before, I am totally dumb when it comes to what these exact type of delays are. So I myself sort of have no clue in terms of what the delay actually happens to be. Which is just kind of it is what it is. Oh, sorry, my wire is getting right in the way. So now we've got the fourth bypass capacitor, or sorry, the third bypass. It's the fourth capacitor. They're all 1 microfarad 0805 capacitors. I think these I bought from Murata. I could be wrong on that. Murata sounds like the right source of where I get these capacitors from. So might have also just been something that fell off the back of a truck and wound up at the college at some point. It's one of those things that happens every once in a while. Let's move on up to the top and put on the big old switches. That's a pretty easy one to be able to do. So I'm gonna put a whole bunch of fluxing agent down on these pads. I actually just recently heard that our lab tech, John, he had to go onto campus recently because one of the companies that is on our college campus had to get some entrance into, well, I suppose I should have prepared the buttons somewhere out here. I have them here. I have 3 of them here. I just have to put them out. By the way, I don't know if you all saw the toothbrushes that I took apart. The Star Wars toothbrushes. Same exact push button on the inside of the of the toothbrushes. The exact same very high quality toothbrush that was on the inside. Now, hopefully, I've got enough heat to be able to just sort of make this work. And if not, well, I'm just going to have to kind of make do here as best as possible. Because this is a relatively larger size lead. So I'm just going to, yeah, I'm going to apply some additional fluxing agent onto this and then just kind of work with it again as we're moving along here. So it's a pretty big, pretty larger size lead, which takes longer to heat up. So if I'm applying, if I am, the whole goal of doing soldering using an iron is to be able to get both the pad and the part hot enough to where it forms a true fusion bond between the two parts. So hopefully that's there we go. There's the third, and that's flowing over very, very nicely, especially with my finger just sticking in the way right there. Sorry about that. So, but anyway, I just recently heard John, our lab tech over at the college, is actually making his way back over to the college. He might also have a setup that he might be doing something similar to this with, so to help out students, and who knows, maybe even provide a little bit of some entertainment, infotainment. What do you call this on here? I don't even know what you call this. I just call it, you know what I call it? I call it the same thing I called it in my first video. Number one, students. We're all students of all types, and I myself had to learn this new online program just to be able to, you know, get good at doing things. And I thought to myself, but there's so much that we do in our classes that involve working with tools, working with our hands, you know? Like, I mean, there's just so much. When they first told us that there was this stay-at-home order, all I could think about to myself was, oh man, there's so much that we need to be able to do that just requires sitting down in front of the tool for a while and just practicing and learning how to do it. I mean, even myself, there are some nights that I stayed late at the college. I know one in particular. Bill used to help me out with the this electronics class as a kind of an assistant to it, and that class went pretty late sometimes. There were a few nights that after class was done, it's like I've got to unwind a little bit, so I'm going to go sit down at an electronics station or some sort of a station all by myself, listen to some nice music, something along those lines, and practice soldering, practice wire bonding, just make sure that I've got up to speed. Actually, the one thing that I probably spent a lot of time doing was trying to hold a part still underneath the microscope. That actually, like, while you're holding onto the part, that's kind of challenging from time to time. You may notice, by the way, I am applying a larger than normal amount of solder onto these pads. Reason being for that is I want that button to be mechanically stable. When you're talking about circuit boards that have a whole bunch of components, the integrated circuits, all of the things like the ICs and the SMCs and anything that's like a BGA, ball grid array type connection, all of the really heavy components are in some ways just as difficult. All those small connections that are on those BGAs, you know, the 84-pin connection on the typical memory unit, all of that stuff, and it still is harder to put a connector onto the board in comparison to all of that. Because not only does that connector have to be connected, usually it's a larger sized part, it has some larger amount of metal mass to makes it where it's harder to solder on, but then on top of that, it's got to be good. It has to be good to be able to be pressed or pulled or connected, disconnected from whatever wire it happens to be over and over and over again. I mean, the one that always kind of bugged me is my own phones with micro USB. They felt fine. Like, you first get them, it's like there's nothing more satisfying than a brand new micro USB, and you plug in a brand new wire, and you feel that, like, it's not a click, because the I is too, like, it's more like a click is what it is. I don't know if there's a vowel for that. There probably is in some Swahili language or something like that, you know. But at the same time, it's not a click. It's something that, like, feels just a little bit softer and not as angry as a click. Now, later on in that life, yeah, there's a click and a wiggle. And there's nothing more frustrating than that feeling of the wiggle, because you put your phone down and you're like, wait, did I put it down just right? Is my phone going to be, charging, or am I going to wake up and it's like, oh, it charged exactly 5%, and then somewhere in the middle of the night my connector got just a little bit used. I hated that. I hated that with a crying passion. Is how I hated it. And so it's one of those, like, even on a circuit board, like, I'm putting an excess amount of solder on all three of these buttons for all the boards, because I want to make sure that those buttons stick. I want to make sure that those buttons stick down, and that even though as many times as I'm going to be pressing them over and over and over again, I want to make sure that they are going to be okay at the end. All right, so now the next chip I think that we're going to put on, I'm going to skip U1 for right now. And if you'd anyone who's watching, if you'd watched in the earlier videos, the problem is with that chip is that you have to kind of get lucky in terms of being able to solder it on. You can't do it with an iron. It has to be done via hot air. And you have to be sort of careful in terms of being able to put on, because the lid of the microphone is very easy for it to pop off. The lid is soldered onto the actual package. So we're actually probably going to solder that on last, is what we're going to do. Now, the next thing I need, I just realized I don't think I have. Do I? I'm going to look at my working board for a second. And I think, yeah, I forgot to grab one of the resistors that I needed. So we'll grab that in just a little bit when I go off to try and find the battery clip. Next thing let's put on then, just because we'll kind of work from the top down, is going to be R3 and R4. Now R3 and R4, on the MEM students, these are not the same R3 and R4 that you all have. My circuit board has something just a little bit different, and that on my number one input for my LM324QT, for the number one pin, you all have it connected straight to ground. I was playing around with the amplifier circuit just a little bit, and I was making sure that I had some degree of variability, and so I did connect it there. But I basically have a 2 mega ohm resistor that's connected up high to VCC in my schematic, and a 120 ohm resistor connected down to ground. This is pretty much 0 volts. But on my board, on my board that I've got, I don't have 0 volts for that board. I instead had a little bit more variability. So what I did was I connected up a 120 ohm resistor all the way down to ground, which is what we're going to attach to. That would be R4 is where that's going to be. So I need a few 120 ohm resistors, and I use 120 ohms kind of throughout the circuit. Namely, this particular capstone project, when you speak into the microphone, depending on how loud you're speaking, certain LEDs will turn up and turn down going on to here. So the LEDs are there's going to be 3 LEDs down at the bottom. Oh, you can't see what I'm doing here. There's 3 LEDs down at the bottom part of the circuit board, which we'll get to a little bit. Oh, there it is. There they are. So there's 3 LEDs down at the very bottom of the board, which we'll get to. They represent different volume levels of which someone is speaking at. R2 is going to need to be a 1 kiloohm resistor is what it needs to be. But R3, let me see now, R3 is going to be the 2 mega ohm. So R4 is going to be where these other ones go. So let's attach everything down to R4, starting with the circuit board that's all the way on the left-hand side. I'm going to put flux on all 3 of the boards. This fluxing agent also, the other nice thing I like about this fluxing agent, it's cheap. Like a 3 cc syringe costs, I'm sorry, either 10 or 30 cc syringe costs something around the range of like $12 or $14. It is very inexpensive. So it's effective in terms of being able to use it on a circuit board. It's effective for things of both chip resistors as well as tall things. Which the nice thing is about chip resistors. Now it's not going to be as nice for these for the 0603 chip resistors. Every resistor on our circuit board is an 0603, and I did that because I'd like everyone to be able to see what those numbers are that are on the board. The nice thing is about this stuff, well, I grabbed a 131 ohm resistor apparently, so it's a little bit off. See that? See what I did? I can just take this fluxing agent and plop the little chip resistor there, and it sticks. Now, that's not so bad for an 0603, but when you start going down to 0201 and 01/05s and like the Imperial system, it takes anything. It takes any small, minor amount of static on you. It takes like 15 electrons, and that thing will not leave your tweezers. And you're going to be like, get off, get off. Wait, no, don't, don't fly off into the ethos because you'll never find it again at that point. You need to be able to have that there. And the tacky flux provides an excellent source by which that chip resistor can attach to it. Even in some of the cases, gosh, that chip resistor, you see what it almost did? It almost just kind of maneuvered on over into that spot there. That would have been kind of a funny thing to be able to see. So yeah, I mean, this is I'm trying to connect this up to grounds. This isn't necessarily like anything like the fact that it's not a 120 ohm resistor. It makes me wonder if my other chip resistors aren't 121 ohms. I'm sort of pulling this out from the hey, who put stuff in here box? So there might be some other kind of things that could be interfering with the way that this is going. You never know. It's one of those, and even in some cases, it's like, oh, I got a chip resistor. Yeah, throw it anywhere. You can just go anywhere you want to. Doesn't really matter at the very end of it. So we got the next chip resistor. Let's see if this one is 1-3. And for those of you who are tuning in and don't remember, yep, another 130 ohm resistor. So this is a code. It may say 131, but remember the last digit for a 3 numbered resistor, that last digit is, oops, sorry about that. There we go. The last digit is the number of zeros that follow after the first 2 of them. So, for what you see right there is 1, 3, and then a single 0 that follows after the 3. So 1, 3, and then a 0 afterwards, making these guys 130 ohms, which would probably make all of them 130 ohms. If I had to guess, I've pulled 2 of them out the same here, and if not, I'll just be something I've got to. Oh, there's some. You see that? You see that? What is that? What is that? There's a piece of crud. There's a piece of crud on the board. What are you? What are you? It's a booger. There's a booger on the board. Is that going to interfere? Is that a biological interference? I don't know. I'm not sure about that. Holy cow. I didn't expect that. I don't know. I'm not sure where that came. Then again, this is coming from my workstation. And my workstation is, unlike a clean workstation, it is a workstation that requires some attention frequently. I'm sure if I actually did clean it, actually no, I did clean it. I think it was last weekend. I cleaned my workstation, and then I couldn't find anything. So that's a little bit of a problem when it comes to that. What I'm doing here. Also, one of the things that someone asked me the other day was, is there any way that I can put an overhead camera somewhere near me? Hey, would you? And the answer is, I'm going to give that a shot using something I think is going to basically work at its cheapest level. So there we have. We have 3 130 ohm resistors that are on there. Now the other ones, that the R3 in my schematic is 2 mega ohms. I don't think I actually have any 2 mega ohms, so I found the next closest thing, which is a 2.2 mega ohm resistor. So I'm gonna pull a couple of these guys out. But yeah, so I've got something coming in the mail that I ordered that should be able to provide a little bit better view, kind of more of like from behind, like my shoulders kind of view, more or less, on what it is that I'm doing here. And I'm gonna give the camera a try. I am not so confident that it's working right now. Right now, I'm just using a basic laptop like just about anyone else's. But I have a lot of people that are telling me like, oh, they'd really rather see like where my hands are. How messy is the workstation? That was my first hesitation. Like, I don't know if I want to show everyone how messy the workstation is at this point. You know, it's just that, or maybe it'll make me clean it up more. I don't know. I don't know if it'll be a thing or not. Let's put more solder wire on here. Let's put a little bit more of this. So R3. Let's see if I've actually got a 2.2 mega ohm resistor. So 2.2 should be 2, 2, and then 5 zeros following. And yep, that's what I've got. I've got a black hair that's floating around. I don't know where those black hairs are coming from. I keep thinking I see like black hair kind of floating around all over the place. I mean, like I have a dog, but his hair is yellowish colored white is what it is. So most definitely not him. I'll come back to that one here in just a second. I'm going to kind of try to see if I can get on a roll. You notice though, folks who are, because I'm going to kind of post this video up to a few places. I found a Facebook group that actually oh, well, now that's upside down. Let me fix that. That actually is all about printed circuit boards, and I was actually really excited when I found that group. I was like, oh, that's cool. There's actually like a professional Facebook group about this, and as it turns out, it seems like it's just a bunch of companies that are all advertising. Oh, look, see, that one says 205. So I do have some 2 mega ohms. They're just mixed in with 2.2 mega ohm resistors, and that's really fair. You know, that's really fair. What about this guy? Are you 2.2? Nope, you are 2. So they are all mixed together in the 2.2. That's probably what it is. I imagine that's exactly what that is. What about you? Are you a 2.2? I'd like to just, oh, well, maybe you were. No, you are a 2.4. Yeah, close enough, you know. Oh, I almost tipped over the entire box there. Yeah, you see what we just went through right there? You see what we just went through? That's my bench. That is exactly my bench. My bench should be storage of. Oh, I didn't even tin that, did I? Let me put that here. This will actually make for good troubleshooting. Oh, it's not a 2.0. It's not the same as the other ones are. It's slightly different than that. Which is one of the things I want to do at the end. I want to get 3 of them working with you all live on camera while I kind of talk about this a little bit. And then come on back and sort of introduce them to my friend the Goblin, who has a tendency to make things not work very well. Let's see. So that's R4. So now we'll come on over here to R3. That's soldered into place. I love the micro knife tip in terms of how well that links up with the side edge of a chip component like that. It just really is awesome. Well, while we're here with the 2.0s, I think last I checked over with the schematic, there is a comparator network circuit. Yeah, here it is. It's not really drawn very well in here. Here's R7, R8, R9, and R10. But R7 also happens to be a 2 mega ohm resistor. So let's just, while I've got the, well, I had 2 2 mega ohm resistors out. I can only see one. I'm assuming that this other one that I've got over here, let's see, what are you? Yeah, you're one of them, so you just sort of flew off and away for a little bit there. Let's see. I've got another one here. Are you 2? I mean, I'd like to keep everything the same before I go into story. No, you're a 2.2. What are you? You're a 2.2. You're a 2. Leave my tweezers. Thank you very much. Let's see. There's a 2.0. There's a 2.0 resistor in there. I think there's actually two. Actually, now that I'm thinking about it, yeah, there are. So the amplifier circuit. So the signal comes out of the microphone, and it's a varying DC signal. The C3R2 combination around the filter, what it does is couples the circuit and removes the DC bias. So you've got a varying DC that goes all the way down to 0 volts. So like when it comes out the microphone, it's 0.8 volts and then it bounces around there. I don't want to amplify up the 0.8 volts. I wanted to reduce the 0.8 volts down to 0 and just let the microphone go up and down a little bit from there, which is what that circuit does. Now that circuit, which has the net list of filter 1 is what that stands for. Filter 1 goes into this part of the amplifier here, which is a circuit that has a roughly a gain of 50. I think 2 mega ohms divided by almost 50K is, or roughly 40, 50, somewhere around there, which actually isn't enough. I'm going to have to boost that up a little bit. That's going to be one thing that I actually have to boost up. But now that I am looking at it, there is a amplifier circuit that needs a chip component there as well. That's around 2 mega ohms. So I might as well bring them all out that I had prepared. And just kind of, some of them might be a little bit off. Actually, I have 7, so I grabbed 1 extra, because why not? You know, why not grab 1, 2, or 5 extra or something along those lines there? You know? And so let's see here. So I need to put this at R5 and R7. Okay, so now we're going to go back to, oh, nope, that's me. There we go. I'm going to go back over to here. And I accidentally brought up my live camera. Oops. Where are you? There's live streaming. Okay, you're all still there. Yay, this is still working. I can do something. This is a master's degree in electrical engineering. Allows me to be a YouTuber at this point. You know? Yeah. Okay. Okay. So R5 and R7, huh? I think those two are actually they're located very close to each other. So that should be an easy one here. I have to give a lot of credit to some of the students in terms of your designs. I mean, I kind of throw my boards together so that they are functional, but they are not very, they could use some better work in terms of part orientation, in terms of, you know, one student in particular actually had every single chip resistor and chip capacitor all facing in the left to right orientation. Now, you don't see that too often in the board industry, because there's just sometimes you're just not able to do that. But when I saw this student circuit, I was like, oh, that looks really, really nice, is what that looks like. That looked really, really, really nice. All right, so now I've got R5, so I'm going to solder what I'm doing is I'm tinning the pads. I am tinning the left-hand pad because I myself am predominantly right-handed. So I am handling the chip components with my right hand while I attempt to keep the knife edge of the soldering iron still. And I'm actually going to move this 2 mega ohm chip component here. Most of these should be around 2. So if they're off slightly, if they are off ever so slightly, I'm not going to be, like this one right here, this is 2.2. I'm not going to be too bothered by that. I'm really not. I am going to try to make all of the rest of them the same, if I can. So R5 is 2, R7 is 2.2. Is that what I'm seeing here? That's what you're seeing? Is that what you're all seeing as well? Yeah? Yeah? Some of the MEM students, if some of them were to, I sent this link out actually to a whole bunch of folks in the MEMS classes. So if one of their 2 of the MEM students, I'll try to get this uploaded by the end of the night tonight, so that one of them could potentially take a look at this and maybe even make a troubleshooting thing in case one of these circuits doesn't work. They might be able to look at this and say, well, why didn't you do this, you prof? You know, why didn't that happen? Oh, there is my chip component sticking to my finger. Okay, what are you? You are a 2.4. Why do I have 2.4s mixed into here? Okay, here's a 2. So that's a 2 mega ohm. We'll put the 2 mega ohm in the correct orientation. We'll put the 2 mega ohm in the correct orientation. Maybe without a giant stalactite on it would be very nice. And let's take a look. Do I have a 2.2? I do have a 2.2. It's kind of nice. Okay, so can you please? No, no, no. Hey, no, hey, come on. Hey, where are you going? Hey, let go. Come on. I'm trying to do a show here, chip component. That's what this count says, right? This is a show. This is TV, right? This is it is what it is. You know, it kind of counts as a TV show. What do you all think? What do you, the viewers at home, think? You know, is kind of what's happening here. All right, so you, what chip component are you? Are you okay? You're a 2. Hey, you will work. You will work just fine. So now we've got a 2. Now, am I able to get, is the last chip component that I got maybe a 2.2? Did I get lucky? I did get lucky. That's kind of nice. That is actually very nice. See that? See what happened there? I got the correct chip component, but I get to stick inside that tacky flux, allowing it to get held into place. And see how easy this is to move in. That's why I really do like this flux. It's I have to get the exact make and model for the Amtech flux. It's something like TC-559, I think is what it is. In fact, actually, wait, do I have it up here anywhere? No, no, and no, I don't have it there. Before the end of the video, I'll try to list what the actual fluxing agent is in terms of what it is. Right now, I just kind of have it in an empty syringe, or well, not an empty syringe, but I put it inside of a kind of a syringe that's easier just for my hands to be able to handle. It does come, I will say, it does come in a larger size. That is a terrible solder job. You see that? You see that? Let's see if we can fix that up a little bit. There we go. Kind of do that, and see, the fluxing agent allows me to do that. It allows me to kind of move that resistor into spot, because the fluxing agent that stays there is more likely going to have a chance to bond up to the spots that are there. Yeah, educational TV show while working on board design from home. This counts. This counts as educational entertainment, and which is, in my opinion, exactly what this is. It's what it was intended to do. It's what it was intended to be a part of with it. Absolutely. Now, for R6 is on the beginning part of the operational amplifier circuit and forms a ratio. In my circuit, I actually have a 47 k-ohm resistor. Instead, I am going to be using a 10 kilo-ohm resistor, which is going to look like a little bit different than all the rest of them. So I'm pulling them out of my little box right now. There we go. Pulling them all out of the box. There we go. Oh, hey, don't fall on the mouse now. It's not a very nice thing. So let me show you kind of what this looks like here. I'm gonna dispense on R6. I'm gonna do the R6s kind of a little bit off camera. One of them was on there, but yeah, here's what the 10 kilo-ohm resistor looks like. So it is green in its color, which tells me that it's got a slightly higher tolerance in terms of its a slightly tighter tolerance, so it has less variability. Although more often than not, if it's marked with less variability, there's usually some sort of a percentage of some sort that gives it to where that higher tolerance actually has a 4th digit. So in some ways, I've never really seen a chip resistor that was green that also had a tighter tolerance than you would typically find to it. So that I am almost entirely uncertain as to what it is. But it was one of those. It was one of those. Hey, I found him lying around in a box. And I don't have any 47 kilo-ohm resistors, so I'll just use these chip resistors instead. Is what I'm using, and they're actually going on really nicely. I don't know who makes these. The bag was more or less try to get that to where it's right in the middle and it doesn't have a huge stalactite sitting on there. Or actually, someone told me the other day. Someone told me that little stalactite that forms, they called it a dog tail, and I was like, it does look exactly like a dog tail. if you point it up on its side, which I know I did in one of the earlier videos. I kind of was messing around a little bit with one of the solder joints, and I got it to, I pulled the solder way out, and I decided to just kind of make a purposeful bad solder joint. And I'm like, it does look like a dog tail. And someone told me that is actually a term, is what that is. Okay, well, how about you stay there? How about I not grab you? Oh, no, how about I do grab you? There you go. Thank you very much. That's not pretty at all. That last one is. The third board is looking more and more messed up every time because I just don't seem to be able to get the whole thing right with it here. Okay, it's coming on the end. Yeah, still got enough with it right there. Keeping sure, one of the things I don't know if you're noticing just off this. Actually, you're probably not noticing. I just noticed about half of what you're looking at in this video is my horribly painted and chalked up wall behind me. So here, let me turn that around. So one of the things I'm doing every once in a while with this, I have limited space. One of the things, the next camera I have will be in here, but I have a solder station where the soldering iron sits over here, and I am cleaning it off. I am taking the brass wire that's in here, and I am cleaning off the soldering iron a whole bunch. And the reason that you want to do that, the reason that you really want to do that, is because there is no sense in soldering with a dirty tip. There's no sense in soldering with any type of dirty tip. If your tip is contaminated or rusted and it's not shiny, then it's going to produce bad solder joints. That's just the end all be all of the whole thing. I've got a spare floating 2.4 mega ohm resistor. Would you excuse me? You are no longer welcome in this show. Okay, so now what do we have left? I think, okay, so now R8, R9, and R10 across every board. R8, R9, and R10 on every board, which surround the QFN chip. All three of those are 1 mega ohm chips, chip resistors. And again, all chip resistors are 0805s, or excuse me, 0603s. The capacitors are 0805s. Now I'm having a hard time grabbing onto my components. What I'm going to do is wet my tweezers down with some alcohol off onto the side, so that way I should be able to get a couple of them at a time, which I am doing kind of off screen. I don't have these in a taping reel or anything like that. These actually didn't really come in one. I'm grabbing several of them at one time and just kind of moving them off to the side because I need 9. So 1, 2, 3, 4, 5, 6, 7, and then 8 and 9. And I'm going to have to check each one of these as well. So these resistors are important for their value. Their value establishes the reference voltages for the 3 comparators that are being used to compare for the sound level. So if these values change, it means that the reference levels of voltages will also change. Actually, across the entire board, they will change. So here is R8, R10, and R9. We'll start with the fluxing agent down, and then we'll start tinning the pads. Got to wait for that beep for the soldering iron to beep on. There we go. All right, so now we're going to come down here. Here's R8, R10, and R9. Oh, R9. There we go. Yeah, R10's got some stuff onto it. Yeah, I still do like, for the most part, I might be off screen there. Sorry about that. Here, come back. Come back onto screen. Come back so you can actually see what I'm doing. There we go. All right, so that is 105. Yep, that is definitely a 1 mega ohm, and we'll let you. It's so cool the way that surface tension brings that resistor right into place. That really is, in so many ways, a neat part about how solder works and how, like, when solder gets hot, the physics of it, how it's attractive. I mean, like, I've been doing this for a while, and I still to this day get a kick out of out of how solder works. Well, that's not. What is that? 310. Uh, Sir, you are in the wrong place. I don't know where you came from. I don't know where you came from. Let's see. 105. Yep, that is a 1 mega ohm. There we go. Tack you onto the other side there just to put you on. I'll come back over with the solder with you in just this little bit. And then 105. Yep, there's another, the last 105. There's another one. There, you see that? Okay. And the last 105 is there. You sitting in place. Yeah, there we go. There we go. Got some other viewers that are coming in, coming out there. Welcome, welcome. Welcome to the show. Talking about circuit boards. Talking about, watch, I'm talking about, one of the things I noticed just now is R7 does not look like that is very well attached. I don't know if you saw that there. I'll come back and touch up the other lines on R8, R9, and R10, the other pads, that is. Let's put some new fluxing agent down. Tin up the wires. Notice, by the way, that the fumes are actually going. I have 2 fans in my laboratory, but one of them happens to be a smaller fume extractor, which is off screen. I actually can't say enough about how important it is, especially if doing any form of lead-based soldering, that there be a fume extraction, even if it's as simple as just putting some fan nearby that will absorb some of the fumes. Even doing that, that's important for being able to work with lead-based solder. Because there are a lot of places that work with lead-based solders for the pure and simple fact that they work well. They work really well. Oh, let go my... Oh, no, don't shoot. No. No, it's considered to be a not good thing if it were to... Well, come on. Would you please fall down? Thank you. Come on. There you go. There are a lot of places that work with lead-based solder for the pure and simple fact that it solders better. It solders better than lead-free solder. Lead-free solder is very difficult to work with, and that's coming from someone out of education. There's another 310. Did I just grab the same one? I must have grabbed the same one. Either that or I've got myself a party crasher. No, I do. There are a whole bunch of 310s. There's a whole bunch of 310s mixed in here. Okay, let me try another one. You're going to be not 310 actually. That's just 31. So rather than having 1 mega ohms, is that a goblin? Is that a goblin that's doing that? John, Matt, Bill, were you any of you aware of this goblin's existence at all? Could be something like that. Well, due to those other components being there, oh, sorry about that. Excuse me. Can you please? Well, we got ourselves a little bit of a conundrum. There we go. I'll tack on the other side here, the other side here, and one last side, putting a little bit of some soldering on the last part of it there. There we go. Much, much better. This is what that is. Yeah. Only use lead. Can't say. Yeah. It's a reliability thing. It really is a reliability thing. Got lead, and it's like, and you're sending it off into space. That I can't imagine the difference between like having something that's reliable in terms of just being inside of a standard aircraft that's going to be like on our, just on the Terran atmosphere, versus something that, needs to survive the temperature transitions that you've got while up in space. I can't imagine. I'd love to hear more about that at some point. That's a conversation that we need to have at some point, over some coffee or some tea or some beer or some scotch or something like that. I could do all 4 of those. That's really what it is. So I only have 1 chip resistor left out of the group that I pulled, and it is a 1 mega ohm, 105. So 1 0 followed by 5 zeros. So now I need to see if I was smart and I pulled anything anymore. Well, there are 2 additional chip resistors in there, so I did not pull everything out. But are they both 105s? And they are. And they are. Can you guys leave? Well, so okay, so there you go. You go down over there. How many times does that happen? You know? All right, so let's put a little bit more. Oh, I already have those. They're already tinned. Oh, that's weird. I just didn't want to. I didn't want to stay in the tacky flux. And they said, no, we really liked the house that we were staying in just now. I am trying to be a little bit more consistent. I know that the resistors are not polarity specific at all. So it really, in the end, does not matter which way you put a resistor. It does matter that the numbers be on top, or the black side of the chip resistor be on top. There is a little bit of a numbering and a color code that's associated with chip components. And so you do need to have that on the top. You can't have the white underside of the chip resistor be soldered up onto the top part of it at all. I'm going to put just a little bit more on the R8 over, which is, that might, hopefully that's not underneath the viewing screen too much. And same thing here, there's R8 on the left hand side, depth perception, there we go. R10 and just a little bit more over there. Okay, looking good, looking good. So all the main chip components around the comparators are built. Now we're going to move on to the LEDs and the LEDs and the current limit resistors. Now for LEDs, I'm actually going to be using something that I actually found sort of lying around. These are going to be, I think the term when I bought these were cyan LEDs, but they more or less just look white, is what they look like. To show you kind of what they look like, let me grab a multimeter out, because I want to look at what this looks like anyway, just to make sure to see if I see any markings on these particular ones. So here, let me move this out a little bit. There's the LED, and there is a green mark on the LED with a triangle that points to the green mark. Okay, so I would be willing to bet, willing to bet that the LED, these cyan, or no, it's not cyan, that's right. It's not cyan, it's ice is what it is. It's an ice-colored LED, and they were bought at a pretty good discount. So when I test this using my multimeter set to measure diode continuity, we can see that they have a whitish-colored light with the black end cathode on the green marked end of the LED. I'm going to put this LED in LED 2. I have red and green LEDs for the other one, but I wanted to test the polarity because now we're starting to get into polarity specific devices with polarity meaning that the if I put it on backwards, I am not using the device that it's originally intended for, and may either break the device, which isn't so bad, or might break the circuit board, which, well, that is bad if something like that were to happen. So now we'll put this on here with tin U. I'm going to take the LED that was actually flipped over. So the cathode on my circuit board is marked with a chamfer, and I'm going to take the whitish LED there and put it in that spot, and put the other side of that, solder that into place there. There we go. Okay, so there's one ice, not white LED, ice. It is actually, they are actually ice LEDs, which that was part of the reason why I laughed so hard. I'm like, that's its own color in the place where I ordered these from. It's actually been the way that I've looked these things back up again a whole bunch of times as well. As I look back up and where are the ice LEDs? And these LEDs, these are 0603 LEDs. that I buy for roughly, oh gosh, I think they are legitimately around, I think, like 5 cents a piece, something like that. They are not cheap by any means. Oops, they are not cheap, but at the same exact time, they are worth it. They are bright. They are very, very bright. Oh, tin whiskers. Yeah, yeah. With the, I think most like lead-free solders are something around 95% tin, 96, 95%, something pretty high with that. With RoHS being the restriction of hazardous substances, which is good for, it's good for things that for your cooking wares and stuff like that. That's fine. I like the idea of not having lead in the things that I mix in my mixers. So but for things that need practical application, yeah, tin whiskers and tin growth, my goodness, yeah, that's got to be a little bit of a nightmare up in space-based applications. I can't even imagine. I really can't even imagine, especially when like you're up and the oxygen levels start changing because you don't have as much oxygen, like you don't have as much O2 when you start entering up into the more satellite parts of there. Not to mention when you you leave Earth, there's not a lot of oxygen anyway, really up there. You start to leave up into, you start going up towards the moon, and you're going to have a hard time finding some oxygen up around the moon. There ain't no oxygen up there. Is where the yeah. All right. So now I've got some red LEDs. These actually do come in a tape and reel strip that I found. And I mean tape and reel strip. I mean like, hey, here's the beginning and there's the end. So it's like not much on the tape and reel strip when it comes to that. These guys they actually almost look bigger than the ice LEDs. Let me bring one of them on screen. Oh, there's two of them coming on screen. So here's the bottom, and there's the top. And we're going to want to test this out. Again, I want to check to make sure that the polarity is correct when it comes to these LEDs. So I'm going to measure this. I'm going to look at it in terms of where the die is located at. Normally, a pick-and-place system, that would be able to look at the bottom. So for this, if I test this here, okay, so the side that the die is on is the anode, is where it is. So I want to make sure that the anode is on the so that the die, that the side that the die is on is actually on the bottom parts of my circuit board. So I want to make sure that the die is down on the bottom part of the circuit board. And so now we're going to move the boards down and over a little bit here. We'll start with this side here. And off screen, I'm just putting the fluxing agent on LED 1. LED 1 represents in this circuit that we're building here the loudest of the three signals. So this represents overall what is the loudest amount of what would be if we were making the most noise. This LED would definitely light up. Now, the triangle that's on the bottom leads me to think that these are actually LEDs from just a very long time ago, previous capstone project. I myself, for the capstone projects, and for those of you who might be tuning in to this channel and you might be saying, what capstone project? What's he talking about? So every single year, the students of my degree, they have to design and build a circuit board that is involving specifications that I essentially give them at the beginning of class, and then at the beginning of class, once I give them the specification, I give them some of the parts, but not all of the parts, if you will. I give them some, but not all of the parts. So a good die is on the bottom, and so what they have to do for this capstone project is they have to design it, both the schematic, they have to design the layout, they have to get their boards stencil printed, pick and placed, and reflowed. Although our stencil printers, pick and place, and reflow system for this part of our 2-year associate's degree, these particular machines are not the high volume standards that you'll find in most places. They don't have They don't have visual recognition systems. They're heavily reliant on operator setup. Even the stencil printers, there is a lot of mechanical setup. They are AMI Presco 435s, I think is what the model numbers are. And if you look that up, what you are going to find, if you look that up, you will find a workhorse of a stencil printer that can take some punches, if you will. It's meant to be accidentally whoopsed with a lot of mechanical settings, but at the same exact time, it's meant to more or less be something that someone uses for the first time before going out into the higher parts of our degree, in which there are larger circuits that are going, or larger machines that are going to be built, more higher volume based circuitry. I think the last one I've got here in my short thing of tape and reel, like that's beginning to end. I think this is green. I'm going to double check. Yeah, I'm pretty sure that this is green. So let me pull, sorry about that. Let me pull one of these guys over to here. Now, green LEDs, the one thing that you can always, hey, would you please, excuse me, would you please let go for a second? So, yeah, I think the one thing, all right, here, so you're coming down here. The one thing you can tell about well, now you can't see anything. Hang on one second. The one thing you can always tell that's interesting, that's different about a green LED compared to a red one, is that a green one, as far as I've seen, have always had two wire bonds on the top part of the LED, and I think that's for handling a larger amount of current flow that it takes to get up to the illumination values that the LEDs require, or at least what they're specified at. Now, I think also, if I'm willing to bet, I bet you this, actually, okay, so let me think now. If the dye was on the anode side the last time, this dye should be on the cathode side. I'm going to guess that this will make it light, and it does. See that? You get a little bit of some green light. Is what we get. With the turn on voltage, so the red LEDs have a forward bias voltage, and that's the amount of voltage that it takes to turn the LED on and get it to allow current to pass entirely through it. That forward bias voltage for green LEDs is around 2.5 to 3 volts. I think in particular for these are actually, I think, around 2.8 volts for the forward bias voltage. If you don't apply enough voltage to the LED, it will just not turn on, and it will not let current pass through it. It will behave like it will behave essentially like a very, very large resistor. Not quite an impedance, but definitely a larger resistor is what it will behave as. So at this point, the dye is actually going to go on the cathode side, is what's going to happen here. The dye is going to go on the cathode side. I'm doing this a little bit backwards because my tools are not in the right hand. I am not a right-handed or a left-handed person, so I have to maneuver around a little bit. Oh, well, that may actually work. Let me see if I can't maybe pull you over. Hey, look at that. Look at that. Smooth is what that was. Smooth. That's about as smooth as sandpaper. What that really was. Gee, you know. Yeah. That's as smooth as sandpaper. That's my motto. You know, that's life's motto right there. At least for me. I don't know about you folks. Now, the other thing, just to point out, on the bottom of these LEDs, there is a triangle that points towards the cathode. And that triangle, I'm going to try to slowly but surely turn it over. That triangle is on the pointing towards the cathode side. I have seen a majority of LEDs, not all, but a majority of LEDs where whatever the marked side of the LED is, that's the cathode. Not every time. Actually, just yesterday, I was looking around at different types of LEDs, and I found some orange LEDs that I had ordered a while back. And the anode is the marked side of the LED. And to my knowledge, that's the only time I have ever seen something like that happen. It's befuddling in so many ways that something like that could actually happen. But it's one of those, like, it is entirely up to the manufacturer for how they want to build it. If they want to go with the grain or against it. Okay, so I have it backwards right now. I have this. Would you please let go? Here, let go for a second. Thank you. Thank you. Let's get that triangle pointed towards the chamfered side of the silk screen. There we go. I need the triangle pointed your way. Thank you very much. Not the best solder jobs in the world. If anyone from my PC is watching, don't follow me in terms of my my solder skills. These are not the same. These are not the same skills of someone who is practiced in a manufacturing art form. I am practiced more or less in a teaching art form, which it might not look too bad. It might not look too bad, but at the same time, I mean, there's some people are out there like I've seen worse. It's like yeah, but I don't think I'm passing anything class. I don't think Chris. I don't think I'm passing anything class 3 to get that up into space. None of those are going to pass at all for space-based applications. So let's see. Now I need a whole bunch of current limit resistors. Now these resistors I have on my schematic as 120 ohms. The first ones I put down was 130 ohms. So in the end, I mean, ultimately, if these things are underneath like 220 ohms, I'm actually perfectly fine with it. I don't even know if I have enough. 1, 2, 3, 1, 2, 3, 1, 2. I don't actually have enough. I'm going to have to reach back a little bit later on. Although I got those, where are those? Where's that 31 ohm resistor? I'll put that guy onto one of these circuit boards. So now what's going to happen is that R11, R12, and R13 are all responsible for current limiting each of the LEDs, and those resistors are going to be all the same, or somewhere, as long as they're above 10 ohms and under 220 ohms, and 10 ohms, maybe more like 22, like between 22 and say 220, somewhere around there, should be just fine. So these resistors, they might be kind of all over the place. I would not be surprised. Well, and the first one I grab is not. The first one I grab is exactly what the doctor ordered. We'll see if we can keep this up. If I was a betting person, if I was me, I would say somewhere there's going to be a whoops somewhere in the mix. So that one's a little bit upside down, but actually this is one of those, like, the word looks the same right side up and the word looks the same upside down. There's a phrase for that. There is a phrase like a thing that for words that look like the same both one way versus the other way. I think it starts with a P. It's been a while since I thought about that. And I can't even think of other things. But if you look at the resistors there, they kind of look the same no matter what. Here. All right, so here's R11, R12, R13 of the second board. So here we're going to see if how much of these resistors are actually the same value here. And if not, I mean, I do have a whole bunch of resistors. I'll just have to kind of float back off camera for a split second here to find what those are. Okay, so this one's 131, so that one's off ever so slightly. I'm heating up both pads simultaneously. Can I get lucky and just hey, I got lucky. All right. That's good luck. That's a good luck right there. All right, now this one right here, that's 131. So all that means is that a higher value of resistance for a current limit resistor, all that means is that the LEDs are going to be a little bit more dim and they will take up a little bit less power, which was actually part of the capstone project, was that the requirements specifically stated that the board be able to work while underneath continuous operation for at least 1 hour. There was sort of a battery capacity requirement that the circuit could not draw too much power, which actually it really reminds me a lot, because we're on the Chris, we're on the space talks here. It reminds me a lot of the old Apollo 13 movie, where they've got to get something powered up on the ship of some sort. They've got to do some sort of power up sequence to where they they can only draw so much power coming out the thing, and they say well, we have to create a power on sequence that brings it back with no more than it takes to power on a a modern day vacuum cleaner is what it was. So always kind of reminded me a little bit of that. But really in the end, when you really think about it, there is so much that goes into a there is so much that goes into creating as little power consumption as possible for even the more modern day based circuits. Like even the more modern day based circuits, there's something to where people don't like it when their batteries run out. Period is really in the big part of that. People don't like it when their batteries run out. Okay, so let's get the 131. This one's got a couple of values which are a little bit different. I just ran out. Did I just run out of the 0603 120 or 130 chip resistors? I'm looking in my container, and yes, I did. Although fear not, I should have. There it is. A box of values of additional chip components. And let's just pull. I'm going to pull another, just a random. I got two of them out there, so maybe if one's not working, then that'll be okay. Do it there. There we go. All right. So now let's attach the third one to it. Let's see what I put. I reached into the 120 ohm side of the bench. So let's see if I can't. And I got a 130. So they're just kind of mixed in between there just a little bit. That's okay. That works, right? That works. Would have been interesting to design around. I know battery drained a lot of folks' batteries drained really quickly, and I really did want to design something this year with a voltage regulator. But I decided to kind of keep things a little bit simple. One, we had a new staff person coming on whose background is in VLSI and microchip fabrication. And we just wanted to get him kind of adjusted to, okay, let's come on back and do some board level design, which is similar in a lot of ways to what he does. Now R2, we have to come back to R2 for a second because I did not have that in my storage, so I'm going to actually pull this out. These are 1 kiloohm resistors. So I've got, let's see here, 1. So the number I should see when I'm looking at this on the microscope here, there's 2 or 1 or 2 or 3. I'm going to pull an extra one out just in case. So the number I should see for R2 should say 102 for a 1, a 0, and then followed by 2 zeros. It was interesting, though. It was an interesting thing to design around because you basically can't have, one person really wanted to have like the brightest LEDs in the world. I said, well, if it drains the batteries out in the span of like, a minute, well, it's not a very efficient circuit at all. And so we designed it to where it would actually work around 3 times as long, I think is where we had it, given the constraints that we have on our circuit board. So it's a little, oh gosh, that's a mess up there. One of the boards, I'm guaranteeing you, one of the boards I'm gonna put a chip component that is tombstoned on the board. Just a real obvious, that happened, on the for the board. So yeah, that's going to be fun. After these chip components go down, that really leaves us with 2 of the more difficult components to actually put down, which I'll be able to do here in just a little bit. So that would be the QFN circuit, the QFN, which is the LM324QT, which is that might sound, for some of you watching, that may sound familiar as a chip. I did like that the chip was in a QFN, and that operational amplifiers really are the basis for how so many different types of circuits really truly work. So it was really kind of a Nice thing to be able to find, so we reused it again. In fact, actually, the unique thing is about this chip is that outside of the LM324QT, the rest of the electronics are actually all housed into the MEMS microphone. All of it. There are no external electronics outside of the operational amplifier. There's no additional chips. This circuit, I lost one of the chip resistors. I didn't lose it, but it's, hey, you come over here. Thank you. There you go. Outside of the LM324 QT, all of the rest of the integrated circuitry is housed within the ASIC of the MEMS microphone. Which, if you check out my video, actually, I open up the lid of the MEMS microphone so we can actually kind of take a peek inside to kind of see what it looks like. All right, now the fun part. the fun part is the U2 circuit. So I'm gonna smear a whole bunch, excuse me, of solder on there. In fact, actually, before I do this, let me take a quick. I need a steady hand, so let me have some coffee. Good stuff. All right, now let's clean up the pads of my soldering iron is getting caught on my bench here, so I'm going to clean up the pads a little bit and then apply some solder on the iron and just tin all of the outside pads going around the LM324. Now, not the big pad. I'm going to take, I've just cleaned off my soldering iron. I am only going to apply just a little bit of solder in this center. I don't want a lot of solder to be housed within the center part of that pad. I really don't. So, and the same thing we're going to follow with all the rest of them. We're going to take the fluxing agent, put a generous amount down, clean it up, activate it, and then start to tin my way all the way across all the outside pads so that they are all tinned. Clean off my soldering iron. That's the big secret. That really is, honest to goodness, the big secret of doing QFNs is to make sure that you do not put a large amount of solder on the central parts of the central heatsink pad, because it's going to create solder balls, it's going to create shorts, it's going to create a whole variety of problems that you really just don't want it to be a part of with your circuits. I'm going to tin again the outside. I'm tinning around the outside parts of them. Hopefully you can all still see what I'm doing here. Making sure that I'm still on screen. Clean off the soldering iron, and then finally put just a little bit. If you over blob the center part, which I should probably do that. I want to just check to make sure that everything else is sort of working correct to it. Otherwise I actually probably would do something like that. Next, I'm going to take a Q-tip, grab another taste of coffee. That is good electronic coffee. I get it from a local place here in Lakewood called the Rising Star. Really good stuff. Highly recommend that coffee spot. I've not yet had a bad coffee from there. So I am applying some alcohol to clean up the pads, because this is one of those soldering jobs that, like, you kind of want everything to be as fresh as you can possibly get it, if that makes any sense. And so it's really easy to make this messed up as well. And I don't want to have that happen. This one's actually, the tacky flux is already starting to become very, very sticky on there. There we go. There we go. All right. So now, throw that out back over there. Okay, so now what we're going to do, this is going to be a hot air rework. In addition to that, so let's see, my temperature for hot air, I'm going to set an airflow to about, 60, and I'm going to set my hot air to 275. Not too hot and not too much airflow to it. So now we're going to take out the QFNs that I've got. And these QFNs I've got in a little tape and reel. Is where those are. And what we're going to do is we're going to do this one board at a time. So I'm going to take the other two boards, and I'm moving the other two boards off to the side for right now. Then what we're going to do is that does look probably very, very messy right now, which most boards do. Like you're talking about doing some boards by hand. Some boards can look really, really messy. I don't have an ultrasonic cleaner yet in my household. So notice also, if you will, that the dot that is in the currently in the upper right, that is going to match with the chips dot, which is also now in the upper right. Can you see the chip dot? And that's going to be, so that's the polarity marking for these two. That's what that's going to be. So what I'm going to do now is I'm going to put a whole bunch of fluxing agent down. I'm going to pay a little bit more attention to this one up close. I'm going to take my hot air gun, which is what I've got right here. That's taking up a lot of power. I can already hear it taking up a lot of power because my fan is somewhat cool. Now I'm going to hold the chip, dab the chip down into the fluxing agent. Now I'm going to start to do a preheat of the board. Definitely feel the heat going right now. Again, fume extraction. So important. And I'm going to kind of wait for so now my solder has melted. And that has sort of, I'm going to wave it around just a little bit. And there we go. That is not so much heat. That is not so much heat that it blows the other components around. Although I am going to check right now to make sure that the other components did not move in that process. They don't look like they did. That chip does not look as centered as I would like it, but the pads sort of allow it to have that level of accommodation to it. The last thing I'm going to do, though, is as a precaution for this, so I'm going to spread some additional fluxing agent around on the side, and then using the knife tip of my soldering iron, I'm going to kind of run it along the edge of the QFN. And what that does is, as long as I don't see any bridges, that's going to supply enough heat to the pads and enough heat to the chip to where that should connect everything underneath it. And this is something that I do. This is a purely visual thing that even, again, most soldering irons, you can't even do this at all. There we go. Okay, one QFN chip. Looks like it's down. Yes, one down, two to go. All right. Next one on there, we've already cleaned it. The pads are already tinned. It looks pretty bleh, what it looks like. I'm going to put some fluxing agent down. Yeah, you don't want to go too hot up in the air. The reason you don't want to go too hot up in the air, and this is a very typical mistake for folks who are doing hot air QFN, and it's happened to me a few times too, where it's like all of a sudden chips go flying off and away. Make sure I have the right dot in the correct orientation. I'm also going to make sure that you let go. Let go. Here, let me grab another thing just to pry you off of there. Excuse me. Thank you very much. There we go. Got that down here. I've got a little bit of some fluxing agent on my hands. That happens, though. It happens in this industry. You can't avoid that. Oh, wasn't tangled up. All right, so I'm going to hold the chip in its place. Start to spread fluxing agent around. I'm doing what's called a board preheat. Although for a board of this, I'm not really worried too much of anything being thermally shocked or anything like that. See that? See? Can't let it go until you watch. See, the capacitor has started to melt, which means that this will This has started to melt as well. So I'm going to kind of give the board a little bit of a tap, 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 tap. Kind of nudge it into place a little bit right there. Lift that off. And again, I'm at a temperature of 275 degrees C at a flow rate of 60 out of 120. So it's about half of the flow. Actually, that's something that's bothered me on this tool in particular. I mean, I love this tool. It's a quick 861DW hot air rework station. I can't say enough good stuff about this tool except one funny thing to me. So airflow is measured in terms of percent on this thing, I think. So then why does it go up to 120? Why doesn't it stop at 100? I've got no idea. I've no idea about that. I've never understood that. I've always just kind of been like, hey, they're just doing what they do, on the guitar amp pedals, like, why does it go up to 11? Well, because 10's bigger than 11. But, there comes a time where you see a percentage thing like that, and you're like, wait a minute now. Come on. Something seems a little bit off about that. I don't know what it is, but something seems off about that. So as silly kind of as that sounds. Actually, one of the things we are definitely going to want to do for the MEM student, that's 2 of them. Now we're going to do the 3rd one. One of the things we are definitely going to do for the students in terms of troubleshooting this board, creating troubleshooting scenarios, we are most certainly going to create a bad situation around one of the QFNs, to where, because I think there's a lot of students. You've taken this class, you've seen some stuff happen from time to time in this class, and QFNs always seem to have kind of the one kind of a scare moment of the class where it's like, oh gosh, that thing is so small. And yet at the same time, there are so many circuit boards out in the industry that have QFN-based packages on them that you're not going to get away from them at all. And at some point, something could go wrong to where it may not work correctly. And you will have to do a hot air rework similar to what I'm doing on it right now. So now I'm blowing on some hot air onto it. Hopefully you can see that. I'm going to move over just a little bit. Well, the solder has already gone to melt under the QFN. A couple of tap, tap, taps. Nudge it a little bit into place. Move it off and away. Yeah, but I'm at 60. I'm at 60 out of 120. So is that 50%? It's not 60%. It's just a setting of 60. So what that exactly is? You got me. You really do got me with that. So I really don't know in particular. There we go. Going all the way around it there. There we are. Okay. And I do realize one of the things I am not doing right now, one of the things I am not doing is wearing my hot air gloves. Call me procrastinative for that one. I just decided not to do it. Okay. All 3 have QFNs attached to them. And all 3 of them are pretty sticky from the amount of fluxing agent that's on them. But that's all able to be cleaned off with some soap, some water, and some other kinds of stuff with that as well. So I'm getting a notification from here. I don't know what that was. Am I losing hard drive space? I might be losing hard drive space. I am recording this whole thing down, and I'm recording it at a sort of a high-ish level is what it is. Okay, so the last thing that we need to put down for all 4 of these is the microphone. And the microphone, well, actually the microphone and a battery clip, which we're going to put the battery clip on last. The battery clip is actually completely on the underside part of the board. Let's see here. We're still live? Yeah, we're still live. Hey, we're still live. Hey, how's it going, folks? How's it going? Yeah, and even then I'll be putting this up a little bit later on. First thing let's do is let's tin all 4 sides, 4 pads. Now the 2 pads that are on the bottom are actually going to be grounded. And I'm going to make sure that they're just about even, because this is another This is another hot air rework, and this one is tricky. This one, the first one I did, I messed it up, and the lid just popped right off. I'm going to attempt to do this one at a little bit more of a lower temperature to see if I can't, because there actually really does not appear to be an easy way for me to be able to get underneath these boards for being able to do this this next particular part. So let's apply a little bit more flux, grab my microphones out of here. So I actually picked out 4 microphones just in case, because I figured one of these might get lifted, if you will, might be the easiest way to phrase what that is. But just in case, I've got one extra one there, just in case. All right. Let's put it to where the dot is going to be up on the top, matching with the silkscreen symbol here. And now the fun part. Please work. Yeah, you know. All right, so now we're going to. Oh, hey, scoot. Hey, where are you going? Hey, come back here. Come on. All right. So now I am going off of instinct on this. You know, I felt something kind of move down. Does that look good to you? I don't know. What are you doing there? There's a large piece of solder wire that just wound up sitting on top of one of those guys. Okay, now we got the next one. I'm still holding my hot air pen, keeping with the same polarity as before, except I picked it up upside down and my tweezers are starting to get a little bit sticky. There we go. There we go. Okay. I just realized I did not put fluxing agent down for the second one here. That's okay. Okay. Oh, I lost it. Where'd it go? Some of the solder looks like it kind of melted on that one, but okay. Going back in. There we go. Oh, no. Gosh. Having a problem with that one. Yep. And it's it has, oh no, it's not, it has not disappeared. It is sitting on the bunny. That is my my little Pols voice symbol. Let's try this again here. Now I have not put, hang on one second. Yeah, let's try. Well, actually, that appears. Is that connected? These are so hard to determine whether or not they actually are connected or not. They are. In actuality, I think these are one of the more harder components that I have ever actually put down on a circuit board. In all complete honesty, I am going to apply fluxing agent to this one. I am going to remember to not be a doof at the beginning parts of this here. There we go. And making sure that I've got the correct polarity, because I do believe if the microphone does not have the correct polarity, you will be doing. Oh, I saw a solder ball with that, so that's a sign that that's melted for sure. If you do not have the correct polarity, I do believe that there is going to be a problem with this. Am I still live? Hopefully I am. My computer doesn't seem to show that I am, but we'll find out here in just a little bit. So one last thing goes on to here. That would be the battery clips that I need to actually put my headphones down for a second to see if I can find some. Just the one thing, the biggest part of this whole thing, the power supply for the overall circuit, I didn't think to grab. Okay, I found one. Yay! I found one floating around in my spare bins of stuff. On there. Oh, there's the fluxing agent. Amtech NC559V2TF. That's what the name of that fluxing agent is. And is the, where's the, I have to have some extra battery. Can't just screw that up. Well, I think I've got some, no, don't have any in there. Sorry about that. Excellent TV programming. I remember something like this once on an episode of Aint. Gosh, do I really only have those guys here? That's what I can find in the immediate time frame. Yeah, that appears to be so. It's really all that I can really find right now for those batteries. Well, okay, I've got one, and I've got a couple of others kind of off to the side right now that I can find here. I'm coming back. Hey, how's it going? You all still there? So, let's do this. Instead, what we are going to do is perform a little bit of a hot air rework on a battery clip off of another circuit. Well, actually, here, I got one. I do have one that is a good battery, if you will. I have one that is here. And let's attach you to the board that's on the back, following the correct silk screen and everything like that. So here I'm going to put down some solder paste down here and here, or some solder fluxing agent. I'm going to put a whole bunch of solder on this particular side here, and then come on over with the. Normally I would absolutely want to. I'm probably doing this right underneath where my beautiful face is. Normally I would want to use a larger soldering iron for being able to do what it is that I'm doing. Again, call me procrastinative. Although I am going to use the larger solder wire that I happen to have here. That should make this just, there we go. And there's the first one all soldered into place. And if I were to connect a battery to this here, hey, look at that. Look at it. We got if I talk normally, the green one's there. If I, where's the light? If I talk normally, the green one's there. Talk a little bit louder, the blue one's there. And hey, talk it up loud, red. Hey. So there you go. Well, did you all see that? Okay. Hey. So there, hopefully you got a chance to see kind of where that is. So that's good. The first one is all currently working. So that's a good thing. Go over to the second. Now, in order to do the second ones and third ones, I don't have an extra. I have like a million. Literally a million of these things in the laboratory at the I know what one person, if John is watching this, because he actually called me this morning, he was asking me if I needed anything, and I was like, nah, I think I got everything back at home, everything I need to do. And I was wrong. You were right. I was wrong. You were right. So now, here, let's just I'm going to take this guy off of here. That's what I'm actually going to do. I'm going to take you and lift you off. There we go. Thank you. And take you on the other side. So this is another chip of just another circuit I have that's sort of floating around. And I'm going to be kind of cheap with this one here, just to I'll solder that first one on, but the other one here, this one, I'm going to take a battery and just touch it to the back terminals of these two, hopefully in the correct orientation so I don't accidentally fry anything. All right, we'll touch this guy to the back part here and here. And yes. Okay, so the second one works. I don't know if you can see that on there. Second one is definitely working. And then lastly, how about a third, just for the heck's sake of it. Hey, oh, did I put it on correct orientation? I always got to wonder about that. Did I have the... Oh, this one does not. Ooh, we have ourselves... Or does it... No, this one does not. This one is not coming on at all. We have ourselves... And that was the first one that I did. I am under the impression... I'm very much under the impression that the QFN chip that I've put onto this first one here is actually not attached. So I'm going to cover it over with a whole bunch of fluxing agent. And I'm going to try the QFN chip again. It's either the QFN chip that I didn't feel right about this. There we go. I kind of... That would kind of help to give it a little bit of a tap, tap, tap. All over it there. All right. That looks a little bit more in the center than it did before. I'm going to take a little bit of some time and run my soldering iron across the chip. And if it doesn't work this time, if it doesn't actually work after this one, I might actually just leave this for the class. What better way than to troubleshoot this in front of the whole class? But let's see here. Let's try this one last one right here. And I'm hello? It is not working. All right. You know what I've got here? I've got something I can actually share with the class to see what would actually happen with this. So, well, anyway, though, 2 out of 3 ain't bad, especially with one that's potentially might need to have a little bit of some fixing here and there. So, but yeah, that's ultimately, thank you very much, folks, for, those signed on. They're looking at this video or anything like that. I'll try to get this posted up so that people can kind of comment on this as well. And looking forward to making some additional videos in the future for not just this circuit, but a variety of different circuits that we've got. I've got some things in mind to just kind of keep people interested in the science and engineering that is electronic hardware. It's a fascinating subject to me, and I'd like to be able to teach more and more about it. So thanks very much, everyone. And hey, leave a comment, subscribe if you're interested, do all the rest of that fun YouTube stuff, that everyone does. So thank you very much also for Bill and Chris for leaving some of the comments that were in there. Thanks so much, fellas. Best of luck to all you folks there. Maybe we can get together sometime when all this starts to change here. Yeah. All right, folks. We'll see you around on the next one. See you later. Bye-bye, everyone. Bye. Bye-bye. Bye.